Hello. Am I audible and is my screen visible?
Yes, but there is lot of disturbance.
But can you hear my voice properly, or is there some problem?
It's it's audible.
Yeah, that is from my ceiling fan. That I can't do anything. It makes such noise, so you have to bear with that. So I would try to speak a little louder so that all of you can hear my voice properly. Otherwise, I can't stop that noise. Yeah, so good evening everyone. Welcome to this NPTEL live session for the course Deep Learning IIT Ropar. My name is Learning-IIT. I am a PhD scholar in the Department of Computer Science and Engineering at IIT Kharagpur. So this is my 9th live session. We will discuss some practice problems on week 9 topics. So in week 9, word representation methods were taught. So some count based methods and then some neural network based methods were also taught. So we will discuss some questions on these word representation models, and if you have any questions or queries regarding these topics, you can ask me during this session. So we will start solving the problems first, and after that if you have any other questions or queries you can ask me. So this is the first question. Which of the following solution constructs a binary tree in learning word representation using prediction based models? So there are three options: negative sampling, contrastive estimation, and hierarchical softmax. You can write your answers in the chat. Vandana says option C. Bemuri Gayatri says option C. Okay. Anyone else? Correct answer here is C, hierarchical softmax. So all these three methods, negative sampling, contrastive estimation and hierarchical softmax, these methods are used to train word representation models like continuous bag of words or skipgram model. So for example, in negative sampling, we along with the context, we use some non-context words also to train the neural network. So that is negative sampling. So those negative context words are treated as 0 class and the context words are treated as 1 class. So these are called negative sampling. Similarly, in contrastive estimation, we replace the actual context word with some different words which should not be the context of the words. So that is contrastive estimation. And in hierarchical softmax, so the softmax computational complexity is very high if we have a large vocabulary. So in that case, computing the softmax would be very expensive. So in order to solve that problem, a binary tree is formed which will have v number of leaf nodes, and v is the number of vocabularies, size of the vocabulary. So the binary tree would be used in instead of computing the softmax from scratch. So it would reduce the overall complexity. So that's why this hierarchical softmax is used in word representation prediction models. Now question 2. So PMI between W and C, W is the word, C is the context, is given by, so there are 4 different expressions for PMI. Which of these is the correct expression for PMI? Vandana says option D. Okay. The correct answer is option D. So PMI of a given word W and context C is originally written as log probability of W given C divided by probability of W. So this probability of W given C can be rewritten as count of w comma c. So the count of w comma c is the number of times the word w appears in the context of c, divided by count of c, and probability of w is given by count of w divided by n. So n is the total number of words in the corpus, and count of w is number of times w occurs in the whole text corpus. So if we put these two probability values into the actual PMI expression, we will get PMI of w given c would be, so this would be log of count of w comma c divided by count of c into, so then invert of that, so n divided by count of w. So everything inside the log, and this is option D. So log of count of w comma c into n divided by count of c into count of w. So this is the PMI between a given word w and a context c. And now question 3. Given two words, humans judge the similarity between the two words, and the model computes cosine similarity between the two words. So this is a method. So which of the following method consider the above approach in evaluation of word representations? So there are four options: semantic relatedness, synonym detection, semantic analogy, and none of these. So this is the approach, and which of the following method uses this approach? Vandana says option B, which is semantic detection. Anyone else? Dr. Ajita V says option A, which is semantic relatedness. Okay. Semantic relatedness is the correct answer, option A. So all these three methods, semantic relatedness, synonym detection, and semantic analogy, all these three methods are used to evaluate different word representation models. So the first model, semantic relatedness, in semantic relatedness method, humans judge the similarity between two words, so they score the similarities between 0 to 1, and then the model also computes the similarity between two given words, and then whichever is closer, the mod basically one or more models compute the similarity between the two words, and then whichever model gives the similarity closer to the human similarity, that model is the better model. So this is semantic relatedness. And then we have synonym detection. In synonym detection, we have one word, and then we will have some related words, and then we try to, using the different word representation models, we try to compute the similarities between the actual word and the other related words. So then the word with the highest similarity is the synonym. So based on that, we can also evaluate how word representation models are able to find synonyms, and based on that we can evaluate those word representation models. And using
Similarity is using synonym detection.
I'm not able to hear you properly. Can you repeat your question?
In case of showing cosine similarity is used detection second.
I still cannot hear you. Can you write your question in the chat? And the third method is semantic analogy, which is where we try to find analogies, like for example, if man is to women, then king is to what, so for something like that. So they say the king is to, it should be queen. So they we try to evaluate whether different word representation models are able to find those semantic analogies or not. Vandana, you can write your question in the chat. Oh, okay, I can see now. Synonym detection also takes cosine. Yes, synonym detection also takes cosine into account, but the approach that I have described here is that for only two given words, first the humans compute the similarity. I mean, humans cannot compute, humans simply judge the similarity between the two words based on their experience, and then the models also compute the similarity. Similarity should always be cosine similarity in this in word vectors, otherwise we don't have that many other approaches to compute similarity. So there is semantic relatedness, that humans judge similarity and the models also judge similarity. Now whichever model gives the similarity closer to the human similarity, that model is the best model. So this is how the models are evaluated in semantic relatedness. But in synonym detection, we have one word, and for that word we have another set of words. We try to find out which word from that set is a synonym of the actual word. So that's why it is called synonym detection. For a specific word, we try to find out which word from the set of the words is the synonym, and based on that we can also evaluate models, which model is able to detect those synonyms better. Okay. Now question 4. We have 500 words in a vocabulary. What will be the size of the one-hot encoded vector for a given word using this vocabulary? Okay, there was some glitch in the network, so it didn't update at the time. We have 500 words in the vocabulary. What will be the size of the one hot encoded vector for a given word in that vocabulary? So there are four options: 1000, 2 to the power 500, 10 to the power 500, and 500. Bandhana says option D, which is 500. So correct answer is option D, 500. So if the vocabulary has 500 words, then the one hot encoded vector of any word in that vocabulary would be of length 500. So for us, the one hot encoded vector would look something like this: all zeros, only one would be there, and other entries would all be zero in that vocabulary, in that one hot encoded vector. So only one element in the vector would be 1, others would be 0. So to represent 500 words in this manner, we would need 500 length vectors. So answer would be 500 here. Now question 5. In continuous bag of words model CBOW, we multiply the input one hot encoded vector with a matrix. What does the ith column of this matrix represent? So in continuous bag of words, two matrices are used actually. This is the first matrix that we are talking about. The one hot encoded vector is multiplied with a matrix. So what does the ith column of that matrix represent? So this is the first matrix multiplication that we do in CBOW model. So there are four options: eigenvector of W, contextual representation of ith word in vocabulary, word representation of the ith word in the vocabulary, and insufficient information. B is the correct answer. Contextual representation of the ith word in the vocabulary. So in continuous bag of words model, the input is the context vector, and the output is the word. So based on the context in CBOW model, we try to predict the word. So the first matrix that is multiplied is the in the first matrix that we multiply with the context vector, it contains context representations as its columns. So the ith column would represent the ith context vector. So it is in the video lecture also it has been shown that if we actually try to multiply the context vector with the matrix, then we will see that it is actually extracting the only the ith context vector of the ith word from the matrix. So correct answer is B. But in the skip-gram model we do exactly the opposite, that based on the word we try to predict the context. So there the roles are reversed in case of skip-gram model. Now question 6. Which of the following is a major limitation of the continuous bag of words model? There are three options. It does not capture the order of words in the context. It is prone to overfitting. It is slower to train than skip-gram model. Bandhana says option A. Okay. Anyone else? Anand says option A. Okay. So the correct answer is option A, that it does not capture the order of words in the context. So this is the full form of CBW is continuous bag of words model. So the bag of words, so that means all the words are put into a bag, so there is no specific order, that's why it's called bag of words. And even the context vector is such that we don't know what is the order of words in the context, we just have ones or zeros. If it appears in the context it is 1, if that word doesn't appear in the context it is 0. So it is a bag of words model, so it does not capture the order of words in the context, so that is the biggest limitation of CBOW model. Now question 7. What is the computational complexity of computing the softmax function in the output layer of a neural network? So you have to find the computational complexity of computing softmax function in the output layer of the neural network, and consider that the output layer of the neural network contains n units in the output layer. So n is the number of units in the output layer. Anand says option C, which is order of n log n. Okay. Vandana says option C, n log n. So the correct answer is option A, order of n. So if you have n units in the output layer of the neural network, so the softmax function is computed as e to the power some z1 divided by summation over e to the power zi. So this I equals 1 to n. So this denominator is summation over e to the power zi, I equals 1 to n. So you have to compute these zi values using something like this, theta I transpose, sorry, theta it should be only theta I xi. Then you have to sum over this e to the power zi. So this denominator computation for n output units would take order of n time, and that's why the overall complexity would also be order of n. And there is no scope for log n, because we have to compute the individual activations for the output units and then sum over them to get the denominator. So we cannot use any log n method in this case. So order of n is the correct answer. Moving on to question 8. Which of the following is or are the main problems of distributed representation of words? There are three options: very high dimensional, very sparse, grows with size of vocabulary. So there may be multiple correct answers in this question. So the distributed representation basically means the count based methods, not the prediction based methods. Anand says B and C, which is very sparse and grows with size of vocabulary. Vandana says all. Okay. Dr. Ajita says A and C. Very high dimensional, grows with size of vocabulary. Okay. So all three options are correct in this question, A, B, C. So in the distributed representation models or the count based models, so the input, whether it's a word or the context, the one hot vector for the word or the context vector is used as the input. So in case of one hot vectors, most of the values are actually 0. In case of words, all the values would be 0 except 1, and same for context, a very few of the entries in the context vector would be 1 or more than 1 in some cases, and all the others would be 0. So these one hot vectors are very sparse, and also the output is also like a one hot vector, so that is also very sparse. So the input and output are very sparse, and the size is equal to the number of words in the vocabulary for both for input and output. So the one hot vector length of the one hot vector should be the size of the vocabulary, and also the output should also be size of the vocabulary, whether you predict word or the context. So it grows with the size of the vocabulary. So if we have 1 million, 2 million words, we cannot really fit it into one neural network. It would not be able to work well, and also very high dimensional. So because the input size is same as the size of the vocabulary, so very high dimensional as well. So all three are correct in this question. And now question 9. What is the objective of the skip-rum method? 4 options. To predict the probability distribution of target words given context words. To predict the probability distribution of the context words given a target word. To identify the most frequent words in a corpus. To cluster similar words together. Vandana says option B. Okay. Anand says option D. Now answer is option B. Okay. The correct answer is option B. To predict the probability distribution of context words given a target word. So the objective of skip gram method is exactly the opposite of continuous bag of words method. So there the input was the context words and the output is the target word. But in case of skip gram, the input is the target word and it predicts the probability distribution of the context words. So option B is the correct answer. This is the objective of skip gram method. So these were the practice problems that I wanted to discuss in this live session. Now if you have any queries or doubts regarding any of the topics, you can ask me.
Can you explain XVD for learning word?
I cannot hear you properly. So are you asking, can we use SVD for word vector representations? You can write your question in the chat. I can't hear your voice properly. So in SVD method, what we do is that first we have this X matrix, which is the co-occurrence matrix. So we have words for each row and columns are for the context words. The co-occurrence matrix, I think you already understand. So the co-occurrence matrix, we do the single value decomposition of X as this U sigma V transpose, I think. So this singular value decomposition gives you this U sigma V transpose, and then this, from this U sigma V transpose, basically this U sigma part will give you the I think each column of this U sigma matrix gives you word representations for different words. So in simple words, this is what happens in SVD. So the explanation, the complete explanation and proofs are given in the video lectures. So this is what exactly is done, is that we decompose the co-occurrence matrix as U sigma V transpose, and then this U sigma part, we can only take the U sigma part that gives us the word representations. Every column of that represents the representation for each of the words. If I am not mistaken, this is what happens, that each column is the representation of a certain word.
Okay. Yeah.
Does anyone have any other questions?
Thank you.
Thank you. Okay, if there are no other questions,
Thank you, sir.
okay,
Thank you.
thank you. So, if there are no other questions, then we can end this live session now. Thank you everyone for joining. We will meet again next week.
Thank you.